Perry. I'm delighted to give this first talk of this scientific meeting 10 years after flyby, and as said, I will be providing an overview of Pluto's geologic history as told with the aid of a global geologic map that I led the creation of, and which hopefully should finally be published by the US Geological Survey by the end of this year. So, yeah, I'm sure many of us here remember this moment like it was yesterday. So exactly 10 years ago, New Horizons flew within 12,500 kilometers of Pluto's surface. We had made some predictions beforehand about what we might see at Pluto, but really when these first images came down, it really just blew those predictions out of the water. It was clear from the get-go that Pluto was a far more geologically complex a place than we had ever imagined. It was clear that there was a very broad range of surface ages, including evidence for ongoing resurfacing, and also that there were a great diversity of morphologies represented across its surface. So there's a great variety of processes that had affected it. So really, in the blink of an eye, we really had to reassess what sort of geology is possible in this quite small and isolated world, sort of in this quite energy-starved part of the solar system. So just a recap of what New Horizons actually saw. This was a flyby, so we only saw one side of Pluto up close, the near side, which is on the anti-Charon side of Pluto. The near side is defined as the part of Pluto that we saw at better than 1 kilometer per pixel resolution. The remainder was at sort of rather worse resolutions in the days immediately preceding closest approach. Another thing to consider is that Pluto has a very high axial tilt, or obliquity, of 119 degrees, so it rotates on its side, and as we flew by Pluto, the northern hemisphere is entering summer, while the southern hemisphere is entering winter, so most of the southern latitudes were in darkness, although we did get a bit of bonus imaging thanks to haze layers in Pluto's atmosphere that scattered sunlight and dimly illuminated the night side, so we got a bit more than we had planned, imaging in the southern part here, which turned out to illuminate some very interesting features. So there are various New Horizons datasets and derived datasets that were essential for helping complete the map. These include the very lovely stereo digital elevation model of the near side that are created by Paul Schenk, shown at the top left here. There was no such topography for the far side. We had to rely on sporadic limb profiles to gauge topography there, as you can see here. And the MVIC and LISA cameras, part of the RALPH instrument, contained spectral maps of Pluto, which sort of allowed us to gauge the distribution of different ices across its surface. So this is the map that passed technical review in October 2023, equatorial scale of 1 to 7 million, 36 units mapped, including set 6 that we decided to map separately on the far side, which we thought was prudent, given the very different, great chasm in data quality between the near and far sides. Also mapped tectonic lineations, superficial overlays, as well as impact craters larger than 14 kilometers diameter. So some parts of the global mosaic, though, were a little bit too ratty, so we left a few parts here unmapped. And so once the map was completed, we then assigned ages to these different geologic units, as shown in the correlation of map units here. So each of these bars represents a different unit, and they each represent the sort of time scale of their genesis and modification, with the oldest at the bottom and youngest at the top. We could define relative ages using cross-cutting and superposition relations between the units, but we could also assign absolute ages with the help of crater counting by my Minister for Cratering, Kelsey Singer, who created this thing called an R-plot here. So each of these, for cratered units, each of these dots represents their position on the graph, indicates sort of their crater spatial density. In this case, more craters and older units at the top and younger ones at the bottom. So We use this to ultimately define 4 geologic periods in Plutonian history, each one sort of home to a specific era of geologic activity. The Birnian, the oldest, from more than 4 to 3 billion years. The Hayabusan, in its kind of middle age, from 3 to 2 billion years. The Tartaran, 2 billion to 50 million years. And then the very recent Sputnikian, less than 50 million. So starting with the Birnian, the oldest period, and also the most geologically active, lots of different things happening. On the map here, I've indicated just with Bs that most of the Birnian units crop up to the west and north of Sputnik Planitia in the middle here. So lots of things happening. Most of Pluto's craters formed, including by far the largest, the Sputnik Basin, which promptly filled with the vast majority of Pluto's nitrogen ice to form Sputnik Planitia, these yellow units here, and where most of the nitrogen ice remains to this day. The emergence of this incredible tectonic system, the ridge-trough system, shown by these purple units here, and also going over the North Pole. The carving of the Sputnik mountain blocks in brown here. Highlands glaciation around the rim of Sputnik Basin, and also mantling events happening, forming these light blue layers to the west of Sputnik Planitia. So the formation of the Sputnik Basin is arguably the most consequential event in Pluto's geologic history. Its outline is roughly indicated by this yellow circle here. It's about 1,400 by 1,200 kilometers across, so it's a bit elliptical, and very soon after forming, in tens of millions of years, it did start to fill with the majority of Pluto's nitrogen ice, and also we know that Pluto underwent true polar wander in response to its formation, sort of not just the filling of it with nitrogen ice, but also we think the upwarp of a subsurface ocean caused Pluto to reorient such that Sputnik Planitia is aligned along the Pluto-Charon tidal axis, as shown in this sort of animation created by James Keane, who led a early study on true polar wander. So as for the actual the basin within the map, it has been since then heavily modified around its edges. I don't think there's really many places where sort of original virgin Sputnik material exists. One of the ways in which it's been most heavily modified is by glaciation, such as this Highlands nitrogen ice glaciation, which we think carved this sinuous valley in Voyager Terra. The red outline here corresponds to the red box on the map there. I would say probably maybe the most well-preserved part of the edge of Sputnik Basin is this heavily cratered terrain on its northwest rim here, which is also home to Burney Basin itself, Pluto's as yet only resolved multi-ring impact basin, which formed soon after the Sputnik Basin did. The other gargantuan feature of the Birnian is the ridge-trough system. So this is an enormous very complex tectonic system. It's aligned along a great circle, roughly north-northeast, south-southwest orientation. Thousands of kilometers long and a few hundred kilometers across. We're not actually sure how long it is. It definitely carries on into the dark southern hemisphere. However, from my mapping, I think it actually splays and kind of peters out around the North Pole. It's multi-component feature. It sort of manifests differently along its length. It shows, it sort of manifests as graben faults, very deep, wide valleys, mountain ranges, tilted blocks, and also large ovoid depressions. And a lot of these appear to have been quite heavily dissected by Highlands glaciation, as sort of shown these fault lines here and these mountain ridges here. They're all quite dissected by nitrogen ice glaciation, and the ridge-trough system also intersects the western half of the Sputnik Basin, and we think this is what was the cause of the giant, the ranges of chaotic mountain blocks that we see here. We think that the crust here, already brecciated from the Sputnik impact, was further tectonized by the ridge-trough system, and then Highlands nitrogen ice glaciation intruded this weakened crust and sort of split off these blocks, which are now kind of grounded in shallow part of the Sputnik Planitia here. Moving farther west from the ridge-trough system, we encounter sort of this heavily cratered terrain in the western near side. It also shows some of the best preserved tectonics on Pluto, as shown by Inanna and Dumuzi Fossi here. In this case, radially oriented, or tectonics radially oriented to the Sputnik Basin, which we think formed in response to loading of the Sputnik Basin with the nitrogen ice. We also see a lot of sort of methane-rich mantled terrains here, probably a few hundred meters thick, and it's sort of often best seen where it's actually kind of eroded, probably by sublimation erosion, as you can see in this fretted mantling material here in Venera Terra. However, if we go even farther west, sort of into southern Vega Terra, we encounter terrain that I don't think has been either mantled or glaciated or really had much happen to it at all. And so I reckon this is probably some of the most primitive terrain we've yet seen on Pluto, possibly even predating the Sputnik impact. So by the end of the Bernian period, Pluto had undergone true polar wander and reached its present polar orientation, and then nothing further really happened to west of Sputnik Planitia after that, no large-scale modification. But it was a very different story for the terrain east of Sputnik Planitia, which saw successive large-scale mantling events. So in the Hayabusan period, in sort of Pluto's Middle Age, we see the emplacement of these sort of this thick mantling material across the terrain east of Sputnik that is shown up in these sort of light pink units you can see here. And this is kind of what it looks like in its best preserved form in Pioneer Terra. It shows what we call an accrescence texture. The methane-rich mantling material has kind of coated the landscape to create this sort of softened, rounded textures here, which you can sort of see is apparent quite well when you compare it to these sort of valleyed, Bernian valleyed terrain adjacent to them, which again we think was caused by Highlands glaciation. So yeah, this is where this mantling material is best preserved. Across most of Hayabusa Terra, though, it's actually a bit less well preserved. So in Hayabusa Terra here, this image, it's sort of the mantle has the same sort of broadly undulating topography that we see elsewhere, but at a smaller sort of several kilometer scale, it shows kind of a pitted, jagged texture, which we think is due to sublimation erosion of this mantling material. So, and then this mantling material was in turn superposed by perhaps the most impressive depositional event in Pluto's history, which we think happened sort of less than 2 billion years ago, which is the emplacement of the bladed terrain deposits in Pluto's equatorial regions extending east from Sputnik Planitia, all mapped in green here. The best place where this is best expressed is in Tartarus Dorsa on the near side here, but based on far side topography limb profiles and also spectral data and also just sort of albedo maps in the far side, we can tell that these deposits actually extend for thousands of kilometers around Pluto's far side. So this is an enormous depositional event of methane-rich material. The deposits here reach several kilometers thick, I think as much as 5 in places, so it's really a massive amount of material represented here. But following this deposition, we think there was a period of sort of sublimation which actually caused it to erode into this bladed texture here. The Tartaran period also saw what I'll diplomatically refer to as a regional scale material emplacement south of Sputnik Planitia, forming two of the most enigmatic features we've seen on Pluto, Wright and Picard Montes. These are enormous mountains, roughly circular in plan form, with these giant depressions at their center. Being planetary geologists, we see what look like mountains with the holes in the top. We think volcanism, cryovolcanoes specifically, and that hypothesis kind of persisted to the present day, but there are sort of some competing hypotheses as to exactly how this cryovolcanism may have proceeded. So I can only, for the purpose of the map, can say with confidence that a big deposition emplacement event happened south of Sputnik Planitia during the Tartaran. And then finally we have the Sputnikian period. So this period, sort of very recent, less than 50 million years, entails the ongoing mobilization of Pluto's nitrogen ice deposits, most of which, again, is contained within Sputnik Planitia here, but there are smaller deposits scattered in craters and depressions farther east. So while Sputnik Planitia has existed for most of Pluto's history, it is just ongoing sort of recycling and mobilization of its nitrogen ice. The most explicit evidence for endogenic geologic activity on Pluto is the cellular plains in the center and north of the Sputnik Planitia, which we think is due to solid-state convection of the nitrogen ice here, just powered by the heat that's still trickling out of Pluto's interior. The southern part of Sputnik Planitia doesn't show any convection cells, probably because the ice is too thin here, but we still see evidence for resurfacing in the form of these sublimation pits here, which also their sort of organization into the sort of thumbprint wave-like pattern indicates flow of the nitrogen ice. But perhaps the most spectacular evidence for flow of the nitrogen ice, sort of especially in terms of Earth analogs, is East Tomball Regio, where we see nitrogen ice that is sublimated from Sputnik Planitia recondenses on highlands up here and actually flows from East Tomball Regio back into Sputnik Planitia as valley glaciers. So it's kind of like a hydrological cycle as on Earth, but with nitrogen in place of water. So that's the end of my half. I'll now hand over to Jeff. So Jeff will talk more about how Pluto's landscapes are essentially they're essentially a record, quite often, of Pluto's climate history. So, Jeff.
Good morning, welcome. I hope I can be heard. Let's just dive right in. Well, I should have acknowledged that, unfortunately, my friend and colleague, Alan Howard, couldn't join us today. His wife's having some minor surgery, but he contributed substantially to the work we will discuss. Okay, let's start. First and foremost, there are 4 different cycles we'll talk about, or time scales we'll talk about today. They are mostly dominated by the role that the volatiles, which are for the most part methane and nitrogen, are going to play. Although there is a minor contribution of carbon monoxide, as many of you know, that also tends to parent the nitrogen in many cases. The 4 time scales we will discuss will be annual, ones that are driven by obliquity and eccentricity, which are kind of like Milankovitch cycles. Some long-term evolution, which we'll refer to as Pluto's Middle Ages, and then the early Pluto. You'll see these all obviously fit into the dating system that Oliver just outlined in his talk. Okay, here are examples of the annual or multi-annuals. Most interestingly, and first of all, the annual cycles are driven by the fact that the very high obliquity of Pluto, and then that in turn evolves as the obliquity changes over several kiloatoms to create effects which affect the surface of Pluto on timescales of a Pluto year or a number of Pluto years, but not an entire Milankovitch cycle. And the most conspicuous, and this may be truly an annual or nearly annual phenomena, is the fact that the north-facing slopes in this particular terrain all have small deposits of methane ice. And that is probably moving seasonally. I suspect if we send a spacecraft back to the Pluto system later on this century, we'll see changes in this material. Likewise, maybe seasonally or multi-seasonally are things like wind streaks. And there's even suggestions of dunes, which have been interpreted, these little ridges have been interpreted as dunes, and they may form on these timescales. The fact that they are setting on top of Sputnik Planitia, which we know itself is a recently formed feature, or at least the surface is constantly being renewed, means these things they can't be very old. They must be forming fairly quickly. I like to point that over annual time periods, it's likely only these minor cycles of sublimation and precipitation take place that are really insufficient to modify large-scale topographic features. Well, here this is quickly an adaptation of a figure that was originally published by Rick Binzel and his co-workers that outlines the variation in obliquity, which has the net effect, and also the fact that Oliver just mentioned, has a very high obliquity to begin with, that you have a situation perversely where you could have the sun shining straight down on the surface over a huge range of latitudes, and conversely, there's only a narrow range of latitudes where the period that undergoes day-night cycles at one time or another during this whole period. And the net effect of this is that over a long time period, over hundreds of Pluto years or thousands of Pluto years, the equatorial regions receive less energy, less sunlight on net than does the poles. Now, Oliver just covered this. These are examples of features that are climately modulated. He just pointed out, for instance, these flow lines, which show the direction of flow, and these are we suspect, similar to crevasse fields like you see on the Earth. Here is a great lobe of recently deposited nitrogen out in Sputnik Planitia. Here you can see bits of of the material with the mainly nitrogen stagnating up here on the highlands. And as you can see the laundry list of things we just discussed, seen here in this image. Now, so again, on relatively short time scales, we see interesting effects, and this mostly reflects work that was done and published by Tanguy Bertrand, who's here in the audience, and his colleagues. And the short of it is that over, you can see the dates, there's the last 500,000 Earth years, and so on, that there's been a net loss of ice in the northernmost portion of Sputnik Planitia, and there's been a net increase in deposition of nitrogen ice here in the equatorial regions. And one of the things that is noticeable about this feature is that the pitting is noticeably subdued, probably due to large amounts of net sublimation taking place in this latitude, as well as, we can show you later, there are flow features which suggest the ice is moving north and terminating here as it is lost to the atmosphere here at the north. Okay, so now here's more examples of events that now fall into the long-term climate evolution of Pluto's Middle Ages. There are a few constraints, as Oliver alluded, that constrain the climate and volatile inventory of Pluto, although widespread volatile distribution is likely to have occurred over timescales significantly longer than the so-called Milankovitch cycles. New Horizons measurements of nitrogen suggest that relatively little of it has been lost to space, and that seems to be at odds with the observation that there's been extensive upland erosion due to glaciation, as Oliver alluded to earlier, which potentially implies that there was formerly much more nitrogen to do work on the surface than there is today. But alternatively, an explanation is that the nitrogen budget has not really changed much over time. It simply has all eventually traveled into Sputnik Planitia and lies basically buried there. Also during these Middle Ages, was formed the bladed terrain. Now, the bladed terrain over a typical million years of Earth history will only have a net erosion or deposition of maybe a meter or two. So since these deposits are much, much deeper than that, in fact, the individual ridges of the bladed terrain are typically around 300 meters high. We do think this process is, or this material is deposited over a long period of time, as Oliver alluded, we do note that it has undergone some erosion, and this erosion process suggests that in recent times, the bladed terrain has been undergoing a certain amount of net erosion. There's also evidence that it extended further than it does today. And so we think what may be going on is that the fact that there is apparently a greater extent of methane deposits than the present, that maybe what's going on here is that there's slow secular loss of methane, perhaps due to things like increasing solar luminosity. And again, Oliver also referred earlier to these crescent terrains. The crescent terrains, also are mostly dominated by methane deposition along the crests and tops of these terrains, the higher plateau portions of these terrains, whereas the floors of these terrains are probably have a substantial deposit of nitrogen, although the methane has somewhat coated it, so when you look at it spectrally, it all looks like methane. And so the interpretation, again, as was alluded by Oliver's work, is that these are long-scale processes. They formed over billions of years, and they, again, reflect maybe perhaps some chaotic evolution, which Oliver's been investigating due to things like true polar wonder and phenomena such as that. And notice that I will state that all these processes based upon models of planetary obliquity really only are valid out to maybe a few 100 billion years. Now, again, features which formed shortly after heavy bombardment. There are a lot of these early time features. There's, for instance, this curious washboarding texture on the surface, which may have been formed somewhat analogous to moraines, glacial moraines on the Earth. Here you can see, again, as was discussed earlier by Oliver, you see lots of this heavily dissected terrain, probably, again, due to very early nitrogen glaciation. So very clearly, nitrogen, at least early in Pluto's history, was up on the highlands and did a great deal of work. And I will now briefly segue to the possibility, as I just mentioned in the previous slide, that things could be far more chaotic than we realized. And there's the possibility, at least, that there could be massive episodic brief excursions in the climate. And some of the tantalizing evidence for that is this feature, which looks for all the world like a frozen ice pond, obviously would be, and whatever what's in it, of course, now is solid. Nitrogen was at once liquid. We don't know, but this is intriguing. This is some work that Alan Stern led, looking at the possibility that, at least briefly, the atmospheric pressure on Pluto could rise to many millibars, which at that situation, you could both be warm enough and atmospheric thick enough to allow nitrogen to be liquid. And at any rate, we think that because there's a pressure melting to nitrogen, that very large glaciers probably have pressure-induced melting at their bases, which probably facilitate their movement and their erosion. So in summary, Pluto's diverse geology is a result of both endogenic and exogenic features, and they've combined to provide us with an interesting distribution of these volatiles, as you've been saying in both talks, of nitrogen and methane over to various degrees over its time. The early Sputnik impact event, as again we've been talking about, really played a crucial event in defining everything about Pluto's remaining geology. In some sense, Sputnik Planitia formation is kind of time zero for the ability to map the history of Pluto. And subsequent depositions of things like particularly methane on Pluto's highlands have tended to be concentrated, as Oliver mentioned earlier, to these regions east of Sputnik, but it forms this long strip. And again, alluding back to my observation or bullet point about the net lack of energy in the equatorial regions, that in combination with the high altitude of the features in which linear terrain was deposited, explains why it's located in just the regions that it was shown on Oliver's map. And there have been, of course, possible late cryovolcanism episodes at Wright Bonds and Picard Bonds, while Sputnik Planitia has been undergoing constant surface renewal since its formation. And finally, the mobilization of volatiles by ice sublimation, deposition, and viscous flow have occurred, as I just mentioned, the 4 different time cycles of Pluto's history, and in some cases reflect both cyclical and in other cases secular climate changes. Thank you very much. I think we're ready for some questions.
Yes, so for questions, if you're in the room, we have 15 minutes for questions. I think it's best if you go to one of the mics in the stairway. And at least for the start of the week, if you could say your name and affiliation, just so we know, especially the people online, know who's talking. And if an attendee online has a question, it's easiest if you type it into the chat, and then myself or my co-chair will read out the question in the room. But yeah, again, we have just about 15 minutes for questions, so ask away.
Okay, now, great pair of talks. Thank you both. I have a comment, and then I have a question for Oliver. The comment is this: when we chose the flyby longitude to fly over at closest approach, we didn't know that Sputnik was there. We knew that there were interesting things, but of course we didn't know that it would be this enormous glacier. And we could have chosen any other latitude in principle, and could have flown by, for example, the other side of the planet, in which case we wouldn't really know from the low resolution images what is here. It's interesting that Jeff said that Sputnik controls just about everything in some sense that's going on in Pluto. And I think it's just fortuitous that we happen to choose that latitude, because otherwise we'd be misinterpreting a lot of things, not realizing what a spectacularly important feature Sputnik really is for the evolution of the planet. My question for Oliver is this. You said in your talk that to the west of Sputnik, the terrain looks ancient and largely unaltered, but to the east of Sputnik, that is not the case, that there's been a lot of mantling. And my question is, what do you think is controlling the difference or the dichotomy between the terrains to the east and the west?
Yeah, very good question, and I think Tongi will probably get onto that in his talk later. Yeah, I talk about this a bit in the text accompanying the map. Something about the east promoted mantle deposition there. I think that's in part due to the retrograde sort of atmospheric current that was set up following the formation of the Sputnik Basin and Pluto's reorientation that sort of carried sublimated nitrogen ice and I guess methane ice as well, sort of around Pluto. And however, it evidently overshot the west, which is quite flat. It's really just the ridge trough system and a few craters there that are sort of the excursions in what is really quite flat topography. I think that for whatever reason, east of Sputnik, following True Polar Wander, was perhaps a bit more undulating topographically. I think there's evidence, particularly in Hayabusa of Terra, for these large sort of depressions. And I think some of Tongi's modeling work shows that these sort of large-scale topographic excursions can sort of promote deposition of volatiles there. So perhaps that was the ideal landing spot for a deposition of volatile ices that were traveling around Pluto in this current. And then once you get a hold of these volatile ices on the surface, it's, as we've seen in work by Alyssa, by this Earl and others, you kind of get runaway effects. You build up more and more volatiles. It just accumulates more, and that would just further starve west of Sputnik. So, yeah, it was probably maybe topography sort of creating an initial sort of preferential depositional episode that just accrued and accrued and accrued. And so you see across the far side the sort of thickness of these deposits just diminishes to get back round west of Sputnik. But yeah, Tongi will help flesh that out later.
Thank you, Oliver.
Yeah, what's interesting about that is, in fact, that intuitively, we were all looking at these deposits initially. We thought that probably sublimation was simply coming up off Sputnik, Planitia, and being redeposited directly eastward onto the Tartus region. But in fact, as Tanguy will point out, it works the other way around. It rises up, travels west, and comes all the way around, and then starts depositing as it approaches Sputnik, Planitia. So, but he'll go into details on that.
Thank you both for a really interesting summary of the geology. One of the features that I remember getting very puzzled by when we had the flyby 10 years ago were those bladed terrain. And you sort of talked about it, but could you give an explanation for a non-geologist? How on earth are these bladed terrains made? How are they these structures and shapes?
Well, we could both do this. For better or for worse, I first authored the paper and discussed it explicitly. First and foremost, they seem to be large deposits which form only on high, standing features at high altitudes. And part of the reason why it's mostly methane is because it's high enough up in Pluto's atmosphere that the atmosphere is too warm for nitrogen to precipitate. So only methane can precipitate at that altitude. But in combination with that is the fact that even at that altitude, only the low latitudes have the least amount of net solar radiation. So over millions and millions of years, a substantial methane deposit was formed at these low latitudes and high altitude locations. And then as the deposit once was formed, then subsequently over some unspecific time, probably hundreds of millions of Earth years, it's now been undergoing some net erosion. We know the erosion rate is about a meter per million years at most, or per Milankovitch cycle. So that suggests that something, probably the increasing luminosity of the sun, is now beginning to etch those deposits and make the blades.
But why
I'll just add that, yes, we think the blades may be analogues to high altitude water ice fields on Earth, low latitude, including penitentes. The alignment of the blades tend to be aligned roughly north-south. They're actually maybe slightly north-northeast, we're not sure. But yeah, we think that there may be sort of much larger analogues to penitentes on Earth. I guess a result of their low latitude, sun tends to come across at a low angle and sort of, yes, form roughly north-south aligned blades as opposed to sort of pits.
In fact, that alignment changes as you approach the equator. When you get to the equator, it looks more like a honeycomb pattern. It's only really very linear as you get above, say, 10 degrees north, where we can see them well in our near-side observations.
Thank you.
Could you get questions from over there? Oh, okay, I'm sorry.
Okay. I want to thank you for this fascinating outline of Pluto's history. I want to ask you a question. Should there also be possibly a fifth, very early, a Charonian? Where does the putative Charon forming impact happen in your timeline?
I don't know, in the southern hemisphere that we can't see. Everything we can't explain is in the southern hemisphere. I guess there's...
That's cheating.
Well, I mean, it's the same reason we don't see the scar of on the Earth after the moon was formed, because these enormous events would utterly reset the surface, and everything we would see reflects events which took place after that early Charon formation event.
Yeah, where's Thea's impact on Earth? Yeah, it's
Pacific
all...
Ocean, I'm told.
Okay,
Is there a
yeah.
limit to the time when Charon can it not have happened more than 100 million years at the beginning of the solar system? Do you have any?
That might be a question that might be handled more on Friday, perhaps in the origins section. Yes, it's yeah. I think it predates pretty much anything we can, any surviving surface on Pluto. Yeah.
Thank you.
Hi, before I say anything, I'm just going to ask, is there anybody online who has a question? I don't want to, okay, not yet. Okay, Bill McKinnon, WashU St. Louis. Yeah, thanks, guys. So Oliver and Jeff, I have a basic question, then a side question. And I wanted to ask if you could say more about the stratigraphic relationship of Sputnik Basin and the north-south trough system, which came first, which came second. And another thing that triggered my interest in your talk, Oliver, was you mentioned things in the far west of what I guess we now call Belton Regio, but used to be called Cthulhu, the old dark region. Maybe these old craters, Edgeworth and Oort, you maybe mentioned that you think they might predate, or something out there predates Sputnik itself, the basin.
Yeah, so the it's an interesting relation between the ridge trough system and Sputnik Basin. There's, I think yes, I have my theory, which is mine, about sort of what the the distribution of mantled, unmantled, and glaciated terrains west of Sputnik, maybe telling us about Pluto's original orientation. The ridge trough system itself, it may well predate the Sputnik Basin. I mean, it's clearly its orientation is independent of Sputnik. However, it does seem, some of its features do seem to cut into the edge of Sputnik, so it may well have continued forming after the Sputnik impact. But I mean, just the fact that it's sort of glaciated sort of along its length, it's glaciated in parts that you simply can't explain in Pluto's current orientation, makes me wonder if it was or low latitude. One of the ideas to explain it is that it was aligned along Pluto's equator prior to true polar wander. I know the true polar wander modelers have some thoughts about that. But yes, so it may well have formed before the Sputnik Basin, but evidently there was still, if it did, there was still some activity that occurred after. So yes, as for the far west, I mean, all I can really say is that nothing much really has happened to it at all. These smooth cratered plains. I mean, one thing I would be sort of curious if, I don't know if you ever get around to doing that paper on the effect of the Sputnik impact, if there's sort of modeling that sort of sees how far you might get a traveling. I mean, the yellow sort of outline I did sort of indicates this crest of this broad ridge that sort of defines the sort of edge of Sputnik and maybe sort of be its ejector. There's a question of how far did Sputnik ejector get, how much did it wipe out. I think out in southern Vega Terra, I think that it seems to me that was sort of shielded. It was too far away for any sort of effect of the Sputnik impact, which, yeah, does make me think that it's quite possible that may be sort of pre-Sputnik. Yes, does that answer your question? Okay.
It's a discussion, you know.
Yes, yeah. Yes, that seems to me like it may be the most primitive terrain we've seen. It's really just cratering and a little bit of tectonics. No real evidence for mantling, even sort of even removal of a mantle by sublimation erosion like we see in Rosetta Planitia. Yeah. Okay.
Okay.
Hi, Josh Emery, Northern Arizona University. Great talks. I'll be asking you for some slides to include in classes about Pluto. So, but my question is, thinking beyond Pluto to other TNOs, I'm wondering if you've thought about what Pluto would look like if it didn't have the big obliquity and obliquity swings in terms of its geology, and then also what level of atmosphere is required to see the great geology that we're seeing on Pluto. And so would we expect that maybe on some of the other TNOs or not?
I'll take a quick stab at that. We believe we can explain the features we see on Pluto with its current atmosphere, or an atmosphere which has excursions which may bring it up to several hundred microbars. You know, currently it's around 10 to 15 microbars, depending on where you're standing on the place. It's what it would mean if it had the low obliquity instead of a high obliquity. Well, it would probably mean that, assuming it had the volatile reservoir that it apparently has, or had at least, you'd probably have very massive polar deposits around the poles by definition, and see lots of erosion at the equator. But unfortunately, it seems all the cool objects we've seen so far, Pluto and Triton, both have high obliquities, so it remains mysterious of what the what a low obliquity world like that would look like. Of course, Triton has other complexities, such as the fact the entire southern hemisphere is bright, even though it should be the hemisphere currently undergoing erosion.
So I think we need to move on. That was our 45 minutes. So Orkon, if you want to save your question for coffee break or something.
Just a comment for Fran.
Okay, fine.
So as per your question about the origin of the bladed terrain, unknown. And I think this afternoon there's several talks that are actually going to pick your interest. So some really new, compelling ideas are going to be presented about that from the French group that's here. So yeah, I think this is a fun debate that we're going to have in the next, not just in this conference, but I think it's going to go on for a while. So yeah, just so check it out.
Thank you.